Okay, so now we're going to move beyond this sort of two-group experimental design and think about when do we actually need regression analysis. So what are the situations where we can't just do this two-group difference of means test or this, also called the t-test? When do we need regression? So the first situation where we need regression is maybe it's still an experiment, but instead of just a treatment and control group, instead of just 0, 1 for our treatment variable, maybe we've got a continuous treatment variable, where it's not just do you have constraining power sharing or no constraining power sharing, but it's what's your level of constraining power sharing, right? Or not just do you have oil under the ground or no oil under the ground, but how much oil do you have, right? So we've got many different levels of the treatment variable. That's a situation where you can't just do a difference of means test between two groups. You've got to look at this relationship between X and Y in a little more of a continuous way. It's also the case that maybe we weren't able to run the experiment we wanted, right? And maybe the countries that have a low level of constraining power sharing are different in many ways from the countries that have a high level of constraining power sharing, right? If we were able to do an experiment, we would go around and we would assign these political institutions to this country and those political institutions to this country and those political institutions, right? We draw numbers out of a hat and randomly assign political institutions to these different countries. And then we would see whether they have a civil war or whether they become democratic, right? Okay, we don't get to do that, right? And we have this problem where a lot of times the countries that score high on our independent variable of interest are fundamentally different than those that score low, right? And so making causal inference about the relationship between our X variable and our Y variable is made more difficult. And so one of the things we do is we try to control for or pay attention to and measure statistically all the different ways that our treatment group is different than our control group, or that countries that score low on our treatment variable are different from countries that score higher on our treatment variable. So we do that by plugging additional variables into our regression equation. Okay, and the last reason we use regression analysis is simply to impress people at parties, because you will find you become very popular as soon as you start talking about statistics in your social circle. So the way to think about particularly just a two-variable regression setup when we're just looking at the relationship between X and Y is with a scatter plot. We visualize two dimensions very nicely as human beings, so we can work on this. So our y-axis here is going to have our y variable, our outcome of interest, which here is GDP per capita. And our x variable in this scenario is our level of democracy. So we're testing the hypothesis here that democratic states, that being a democracy causes you to be wealthier. You have higher economic growth over time, you become wealthier. Right? And what I've done is I've just drawn a random sample of countries. I think I did this for maybe about the year 2005. And I just plotted their level of democracy on the Polity 4 scale, which runs from -10 to 10, and their GDP per capita in 2,000 constant US dollars. And so in this particular random sample of countries I drew, I don't have any super rich countries. Nobody's richer than about $15,000 per capita. And I don't have any extreme autocracy. So the Polity 4 score goes all the way down to -10. The most autocratic state here scores a -6. So, this doesn't cover the full range, but it's the sample, and we're going to estimate the relationship in the sample. Okay. So how are we going to think about estimating this relationship? The sort of the workhorse regression, we're going to do a lot of different flavors of regression in the lab, but the workhorse regression model is called ordinary least squares regression. And this is a form of linear regression, which means we're going to fit a line through this scatter plot, right? We're going to assume a linear relationship between X and Y. Very strong assumption, but it's one we're going to use. And usually what our theory tells us, what our theory predicts, is it predicts something about the slope of the line. Is democracy good for growth, in which case the line's going to be positive, and the more democratic you become, then the wealthier you become? Or is democracy bad for growth, in which case the more autocratic you become, the less wealthy you become, right? So we're making predictions about, is this line have a positive slope or a negative slope? And the null hypothesis is usually that that line is dead flat. Okay. And when we say this is ordinary least squares regression, we're talking about, we're trying to make a line of best fit. So we've decided we're going to draw a line, and we're trying to draw the best fitting line. And the way to think about this line is that this line is actually a set of predictions, right? It's predicting for any level of democracy, based on that information, what's the predicted wealth. And when that line goes right through a point, then that error is 0, right? We made the perfect prediction. We predicted they were going to have $6,000 per capita GDP, and look, they've got $6,000 of per capita GDP. But usually our prediction's a little bit off. And when we think about drawing a line of best fit, we're trying to take the distance between the line and each data point and minimize those distances. But here we actually minimize the squared distances. So we take our prediction minus our observed value, and then we square that, right? And then we add up all those squared errors. The line that minimizes that sum of squared errors is our line of best fit. And so when we're estimating a regression equation, we're trying to draw the line that minimizes those squared errors, right? And so we're drawing a line. We're trying to draw a line that goes sort of through as many of these points as possible, or close to as many of these points as possible, and minimizing those squared errors. And because we're minimizing squared errors, it means that outliers, if we drew a line of best fit like right here, these large distances, the fact that we way underestimate their GDP per capita and their GDP per capita, means that those couple of outliers are going to be really influential. We're not going to get into that role of influential outliers too much in these lectures. We're just going to flag that for you as you're thinking about least squares regression. But we're going to, as we're doing this, right, we're writing a regression equation, right? So our regression equation is going to be our y variable, right? We're really going back to like algebra here in middle school, right? Where you've got the equation for a line is y equals mx plus b. You may or may not remember that, but y equals the slope times your x variable plus the y-intercept, right? So that m is your slope, and this b here is your intercept. We're going to sort of rearrange these terms a little bit for the regression equation, but it's the same dang thing. Your y, your outcome of interest, is your GDP per capita equals your constant term. This is the b. This alpha is what used to be the b in middle school. And then you got beta, this is your m, and this is what we're usually really focused on. This is the slope. And we're focused on it, remember, because our hypothesis is, is this a positive slope or a negative slope? So we pay a lot of attention to this regression coefficient, this beta, times our x variable, right? So mx, beta times x, right? And then plus some error term, because we're working with real data, and our line does not fit our data perfectly. We have these errors. Okay. So when we go forth and we do this, when we ask a statistical program to fit a line of best fit through these data, it's going to look like this, right? And you'll see we've got an error of almost 0 here, slightly larger error there, an error here, right? So if we have, and you'll see also, if we've got a Polity 4 score of -5, actually our predicted GDP per capita here is negative. So, we may want to think about slightly more complicated regressions that bound the y variable at 0 here. We can make our life more complicated, but this line is all predictions. If you've got a super democratic country, we're going to predict that you make about, $6,500 a year, right? Again, way underestimating what these countries actually make, right? So we don't make perfect predictions all the time. We can't. The data's all spread out. But this is a line of predictions. And where's that y coming from? So, I'm sorry, where's that the constant term coming from? Where's that alpha coming from? So alpha is the predicted level of your dependent variable where your independent variable is 0. So that constant term is not something we usually interpret because we don't really care too much. What we're really always focused on in this series of lectures, but in social science in general, is really on that slope variable. So what we're really interested in is trying to tell, are we sure that this slope is positive and not 0 or negative?